Okay, so this video is just a reference for myself in the future to remember how these level rules works out. So let's say we have stream which has some composition, okay, set, and with some mass flow, and we want to split that in a flashed in a flash distillation, and we're going to get some liquid and some vapor, some liquid. Of course, this one is going to have some HV, and this one HT, right? I mean, this one we could say this is Y, but okay, let's say we actually condensate that. Anyway, it's not important, it's the same concept. So if we set up the mass balance and the component balance, we get this. Okay, this is the basic thing. Now let's plug this MF into the second one, and we are going to, and then we are going to combine the V's and the L's. So we end up with something like L Txy minus LH equal to V HV minus Txy. Okay, just looking at this, we can go to a, let's say we're going to say in this case we have this. So this is the T as this diagram, Txy. It could be as well Pxy, but the difference is that in this case we have the pressure is constant, and in the other one temperature is constant. We will see how that works out. But what I want to point out here is that here, of course, you can see that the saturated pressure, temperature, of component A is higher than the saturated pressure of component B. Okay, these are the saturation pressures, which means here you have pure component, component A, right? And here you have pure component B. Yeah, sorry, just to correct something, like here actually we have pure component A, and in the other one we will have pure component B. So what I want to point out here is not that, but that first of all, if you have the temperature diagram Txy, here we have vapor, here liquid, and here the mixture. And if we had, for instance, pressure, so instead of having the liquid here, we will have pressure because, volume, because at lower pressure we'll have more vapor than liquid, right? Okay, anyway, so what I want to say here is that, let's say this is the feed, okay? This is the feed, and it's a mixture in this case, or it's just any state. It doesn't need to be the feed, but let's say this is the any state. Yeah, sorry. Let's try to do this like that. Yeah, maybe it's not that clear. Let's change this point. Right, instead of that, let's put it here so it's more clear. So of course it's an example that I'm inventing though, so it doesn't need to be like perfectly invented. So here we have the composition of the, so what would that be? The liquid, right? And the liquid is the bottom, and here the top, so it's of the vapor. So what I want to point out here is that L times this distance. What is this distance? If you see, this is the point Z, and this would be, this distance would be Hz minus this one, which is exactly what we have here. So it's going to be A. So L times A is going to be equal to V times, let's say, C. Okay, this looks like L as well. L and K. And what is K? K is this distance. That's the level rule. So we don't need to know anything else about this right now. But let's move to something a little bit more complicated, which is how to use the enthalpy Txy diagram for deriving this lever rule here. So first thing we need to know is that if we do the mass balance and the energy balance of the entire column, the top and the bottom, we will end up with a set of equations. And for this set of equations, we are going to use this term, which is the heat flow at the top of the column, which is nothing more than the let me show you real quick. So you have the top of the column, you have here your condenser, some recirculation, here you have some vapor coming. So let's say this is the stage 1, okay, so which is going to be the last stage. So here you will have the vapor coming from stage 2, liquid coming from stage 1, right? And here is going to be the amount of distillate. Okay, so this is called the heat flow at the top of the column, which considers how much energy flows here at the top, at the very top. Okay, so this is going to be an important point, because I mean, if you think about that, that point, which means here, is going to have the same concentration at the distillate as the distillate, right? So the distillate, we know it, which is here. We know this point needs to be somewhere there. Okay. What else? We know this value, we know it, right? Why we know that value? Because it's the value here. And we know that after, I mean, it depends, but if we are using total condensation, it would be this point right here, right? This is what we call Txy. That means if we can calculate this value and this value with some mass or energy balance, we will have QC over ME. This is that distance, and we can locate this for this point. Doing the same at the bottom, we will have something like the bottom, whatever, let's say something like that. It's going to be H of the bottom, let's say bottom with B, minus Q of the reboiler over M of the bottom. So basically, this one at the bottom, you will have boiling liquid. That's quite normal. You know this value, which is HB, and from this one you can subtract QR over MB, and you will get it right here. What it's important to point out here is that this point and these 2 points are going to lay on the same line. Okay, wait a second. Same line. And same as the feet. So let's say we have the feet here, edge of the feet. So we know, of course, that the feet is going to be somewhere here. Okay, that's really useful to know it. But anyway, let's just remove a little bit from here. We don't need this. Just that was to locate the point. Okay. Knowing that, we need to know as well that, and now is where or when the lever rule plays a role. So this distance, the entire distance from here to here, we can call it like enthalpy of PA, right? Minus the enthalpy of E or R or whatever here, right? Or maybe better, let's call it enthalpy of the liquid, because it's going to be for all this. I mean, it's going to vary, but of course it's going to apply always. And then enthalpy of this pole minus the enthalpy of the vapor. Then if we think about how this is going to work with concentrations, we can say, okay, the enthalpy of the distillate minus the concentration fraction, the what is called composition fraction, over same minus HV. So this is going to be the level rule. Okay, this is what we are going to use. And why this is important? Because we are telling them that the P, this point, is going to be on the same line as this liquid, always as the liquid, right? And this point is going to be, I mean, it's important here to point out that this is the liquid coming from unit 1, from stage 1, and this is coming from stage 2. Okay, this is important to say. And this is what we call the intersection lines. Okay, because here in this diagram we will have some lines that are coming with the diagram probably, which are isotherms and are called wet lines. And these wet lines are going to represent, I mean, they could represent different things, but let's say they are just isotherms in this case. Okay, don't want to go much into detail of them. Okay, and then the question is, how do you know what's going to be the first point here, meaning this one, right? Yeah, so look at this part. So you know that this vapor coming here is going to have the same composition as the vapor coming here, right? So okay, sorry, as the liquid coming going out from the unit. So you know this point. Then the question is, what is going to be the point, right, of the liquid, this liquid? And you can answer that, for instance, using a this kind of diagram. Let's say you have this diagram here, and you can locate this point. Okay, you can locate this point, and which is this one, right? And you can find the location of the value in equilibrium, which is going to be this one is in equilibrium with that one. And then you are going to come here. Of course, this is not a scale, but when you go up, you're going to be somewhere here. And this point is going to be the composition of L1. Okay, and we said using this level rule, then you can come from this point to this point, right? And that's how you end up knowing that this point here is going to be V2. And then you do exactly the same. You go down, right? You are somewhere here, right? You know, I mean, of course, this is not correct. This is not the correct representation. So, but it would be, of course, less concentrated, right? And then you read the X composition in equilibrium, because, I mean, this stage, this liquid living here, this vapor living here is going to be in equilibrium with this one, right? And then after that, you go up and you're going to know L2. And so on and so forth. Oh, forgot the line. Okay, let's say we already did this part, and you need to keep in mind that I mean, to the right of this line that connects the pole of the stripping section and the rectifying section, this is going to be the rectifying section, of course. And below that, if we see the column, it's going to be something like here, this section. This line is going to be the same line. And then let's say, okay, you already know B4, which is going to be the one that is coming from the 4th unit, and you want to know what's the L of that one. Okay, then it's not a problem. Then you can come here, of course, again, you do the same, and you get that L4 is going to be somewhere here. So be careful because now you are in the stripping section, so you won't use this pole anymore, but the pole of the stripping section. Till so this is going to be, of course, what I said, L4, right? It's going to be B5, and then you do exactly the same, and you get, I don't know, here, right? So pay attention that this is vapor in the fifth one, and this is going to be the liquid in the fifth one, right? So what you need to do then is to measure this distance, and then, I mean, like to do some calculations here with the proportions to know how much of this unit is needed. It's not the entire unit, the entire stage, sorry, I always say unit, but I mean stage. And I believe that everything you need to know about the lever rule, how to use the lever rule for this kind of representations, these two, the Txy, which is equivalent to the Pxy, and the enthalpy Xy. Okay.